Hi everyone, this is your lecture video on section 10.6, the chi-square test for goodness of fit. So let me provide you with a little example here. Let's suppose that we had a list of values and we wanted to know if those values were from a specific distribution. So an example problem that we're going to work on in this video is the following. A school principal claims that the number of students who are tardy in her school does not vary from month to month. A survey over the school year produced the following results. Using a 0.05 level of significance, test a teacher's claim that the number of tardy students does in fact vary by the month. So in this problem, the teacher's claim is that the number of tardy students varies by the month. The principal believes otherwise. The principal believes that the number of students that are tardy each month, right, is the same. If that's the case, then the probability, like if we believe the principal, right, if the principal is correct, the probability that a student is tardy on any given month is 1 out of 10. So for any given one of these school months, right, so we're assuming here based off this table that the school is not in session in June and July. So if the school is not in session in June and July, then there are only 10 months to choose from. So the probability that a student is tardy on like September, for example, would be 1 out of 10. This is for an individual student. Now, if the principal's claim is true, that would mean that these sample values, they came from a uniform distribution. A uniform distribution is a probability distribution where the probability of an outcome is the same for all outcomes. Now, bear in mind that the principal's claim is not what we're doing the hypothesis test on. It says here in the problem that we need to use a 0.05 level of significance to test a teacher's claim that the number of tardy students does in fact vary by the month. So the question is, how do we tackle such a problem using hypothesis testing? To tackle this kind of a problem, where we're trying to see if the sample values come from a specific distribution, this is a hypothesis test that's going to involve the chi-square test for goodness of fit. There are two scenarios to consider when you are tackling these types of problems. When the theoretical probabilities for the various outcomes are all the same, the null and alternative hypothesis for the chi-square test for goodness of fit are as follows. Your null hypothesis is that the probability of any individual outcome is the same regardless of the outcome. So our sample problem lands in this first scenario here. The alternative hypothesis is that there is some difference amongst the probabilities. Before I read the rest here, going back to our problem, the sample problem, the principal claims that the number of students that are tardy in her school does not vary from month to month. So the probability that a student is tardy on any given month is 1 out of 10. It doesn't matter which month. The teacher's claim is that the number of tardy students does in fact vary by the month. So we are landing here in this first category. Your null hypothesis here in our problem is that the probability that a student is tardy on any given month, month 1 through month 10 in a school year, is the same. The teacher's claim is this alternative hypothesis. Now, what happens if those probabilities are not the same for each outcome? If the theoretical probabilities for the various outcomes are not all the same, each probability must be stated in the null hypothesis. So in this case, the hypotheses are as follows. Your null hypothesis is P1 equals the probability of the first outcome. P2 is the probability of the second outcome all the way through P subscript K, the probability of the kth outcome. Your alternative hypothesis is that there is some difference from the stated probabilities. So K here in these problems, K always represents the total number of possible outcomes for each trial. You can also think of this as the number of categories. So in our particular sample problem, the total number of categories is 10 because there are 10 months to choose from. When performing hypothesis tests in this section, we will use the chi-square distribution. I drew a quick rough sketch here of the chi-square distribution. This is a distribution that is skewed to the right. Its key defining feature is the degrees of freedom, denoted by df. The degrees of freedom for the chi-square distribution that we're going to be using for these problems is defined as k minus 1, where k is the number of possible outcomes for each trial. Every chi-square goodness of fit hypothesis test we do in this class will be right-tailed. So your rejection region is the region to the right of the chi-square critical value based off of the level of significance alpha. Your fail to reject region is all of the area to the left of your chi-square critical value, where your chi-square critical value is denoted by chi-square with a subscript of alpha based off of the level of significance alpha. In order to tackle these hypothesis testing problems with the p-value method, you will be using the chi-square goodness of fit test. It's called chi-square GOF test in your graphing calculator. To access this command, you will hit the stat button, go to tests, and then go to chi-square GOF in capitals test. In order to use this command, you need to enter in two lists into the graphing calculator. The first list is a list of observed values that comes from the sample data. The second list is the list of expected values. So I didn't finish the sentence. The second list is a list of expected values. Oh, I did finish the sentence. I'm sorry. It's on the next page. The second list is the list of expected values, assuming the null hypothesis is true. Each entry in this list of expected values is defined by the following. The expected value for row I equals n times p sub I, where n is the total number of sample values and p sub I is the probability of the ith outcome. Now bear in mind, you're dealing with two letters here that involve the sample data. N will always represent the sample size. K represents the number of categories or outcomes. So let's go back to our problem. I'm going to reread it from the beginning. A school principal claims that the number of students who are tardy in her school does not vary from month to month. A survey over the school year produced the following results. Using a 0.05 level of significance, test a teacher's claim that the number of tardy students does in fact vary by the month. So what's the null hypothesis? The null hypothesis is that the proportion of students that are tardy each month does not vary from month to month. So the probability that a random student is tardy on any given month equals 1 divided by 10. Where did this number come from? Let's just start with like the month of November. What's the probability that a random student is going to be tardy in the month of November? Well, if they're tardy, the only way that they can be tardy in the month of November is if they're tardy in the month of November. So that's where the numerator comes from, the 1. The denominator comes from the total number of months that you can choose from in this list. We're not looking at an entire year. We're just looking at a school year for this particular school. And apparently this school is in session 10 months out of the year. What is the alternative hypothesis? The alternative hypothesis is that the proportion of students that are tardy each month varies by the month. The more general way to say this for any particular problem is that there is some difference amongst these probabilities, p subscript 1 through p subscript 10. Another way of saying it is there is at least one of these probabilities that is not the same as the others. Okay, so what do we do? You see this theta. Let's try it again. You see this data table that's given to you in the problem. You need to first enter in that as a list on your graphing calculator. So I did that here in list 1. What's next? The next thing that you need to do is you need to enter in a second list, which consists of the expected values. So this list of expected values is based off of the null hypothesis. What are those probabilities? So for our particular problem, the probability of any individual outcome is the same. It's 1 out of 10. So your expected values will then be the sample size. In that data table, there was 125 students in total. So each expected value is going to be n, 125, multiplied by the probability that a student is tardy on any given month, which is 1 out of 10. So I entered 12.5 for each of those. So this is what, like in general, what your list should look like. One list consists of the observed. The second consists of the expected. Now what? So I'm going to hit stats, go to tests, go to chi-square goodness of fit test. Oopsie. Enter in your observed list, your expected list. You need to enter into the degrees of freedom. So going back to our problem, there are 10 months to choose from. That's the number of categories K. So K in this case is 10. So I should write that here for our problem. K equals 10. So your degrees of freedom is K minus 1. So 10 minus 1 is 9. And then you will hit calculate. You have your test statistic at the top and your p-value right below that. So your test statistic for this problem is 15.56. Your p-value after rounding is 0.0767. So since our p-value is greater than alpha, we will fail to reject the null hypothesis. So at the 0.05 level significance, the evidence does not support the teacher's claim that the number of tardy students varies by the month. Alrighty, everyone. That is going to wrap up our lecture video for this section. I will see you in the next one.